last two sections on chapter 5 is talking about total internal refraction, and then we talk about the fiber optics. Ladies and gentlemen, total internal refraction have a short name. It means TIR. Total internal refraction, or TIR, can occur when the light travels from a medium with a high index to index of refraction to one with a lower index of refraction. So we demonstrate that in a diagram. The following is a diagram to demonstrate that. When the light travels straight on along the normal line, there's no deviation. When the light travels with an angle going into a point, in which case is from the high index to lower index in this diagram. In this diagram is N1 larger than N2. N1 is larger than N2. If N1 is larger than N2, the instant angle, in which cases we like to say theta 1 and theta 2. In which cases theta 1, theta 2 is going to be larger than theta 1. Theta 2 is larger than theta 1. That means when the light travels like this, the angle come out from the medium in the N sub 2 is going to be larger than the theta 1. So if you're making the theta 1 larger again, so the theta 2 even more larger. So until you're hitting an angle, in which case the refraction angle of theta sub 2 is going to be reached to 90 degrees. This angle we call the critical angle. Theta sub c is considered as the critical angle. How critical this is? That means right after the angle larger than critical angle, the light ray cannot go into the lower index medium, but going to be totally refract to the original medium. This phenomenon is called total internal refraction. Then how you find out the critical angle? That means n1 sine theta 1 equal n2 sine theta 2, and theta 1 equal theta sub c, the theta sub 2 equal 90 degrees, just in these cases. And n1 sine theta sub c equal n2 sine 90 degrees, then sine theta sub c equal n2 divided by n1. So that sine theta sub c equal to n2 divided by n1. And theta sub c equal to arc sine of n2 divided by n1. So this, after this, the light ray, after hitting a critical angle, the light ray is totally reflect the original medium. We like to take advantage of this total internal refraction and building a light tunnel. Suppose we have a tunnel like this. Either consider this like a square block. Look like this. When the theta is larger than theta sub c, so this angle is equal to this angle, have a total internal refraction. And this angle theta again, because this surface and this surface is parallel. So the light ray, after hitting the angle in the surface, larger than critical angle, then equal to totally have occurred TIR. So this is called total internal refraction. And finally getting out. So no loss whatsoever. This is the basic theory, theory of fiber optics. Dr. Go utilized this for telecommunication back in 1960 and 1970. And then after a few decades, the people recognize his theory and building up a lot of fiber optics communication gadget. So now they give him the Nobel Prize. Anyway, the fiber optics basically is come from total internal refraction. That's it.
Okay, got it.
Okay.
Sure.
Yeah. Today we're going to cover the chapter 25, in which cases it's called refraction and refraction of light. This is the first chapter. So for the Physics 31B classes. 31B class we'll arrange it so that we can cover the optics first, in which case is basically is using algebra and trig. And then we go into chapter 19, electricity. Electricity is involving a lot of derivative and calculus. So by starting easy, so everybody feeling better. So first we want to talk about light. The light have, the nature of light have two characteristics, like a dual nature. Dual nature light. Just like most of you have a dual nature of citizen. Some of you come from Korea, some of them you come from China. So you have Chinese citizen or Korean citizen. At the same time, you immigrate to the United States and you have American citizen. So American, Korean, and Chinese, and American. So it's dual nature. So in these cases, the light is sometimes behave as wave. When it behaves as a wave, the light propagates like a wave. And then basically is one point light source will spread out. And then each point on the wavefront become a new light source. So that's one way behaves as a wave. We treating the light behaves as a wave, then we using that as a called wave optics. So when you're treating the light as a wave, the light basically is spread out like that. Then another nature of light is behave like a particle, like a boson. The light is travel as a straight line, travel in a straight line. So when you travel as a straight line, we like to define that as a ray, R-A-Y. We're using the ray model to describing the light traveling. For example, in this cases, we're using light ray. Light comes out from a point, is shooting as a travel as a straight line and go through lenses and then focusing. We're using the ray model to discuss about the nature of light, and that body of knowledge we call the geometrical optics. Just like as you can see, when the light travel opening, it goes straight as a point. And when the light travel as a very small point, it spread out, but at the same time, the light travels as a ray going along for each ray. So on the top of it, we'd like to study how does this light ray interaction with material. For example, with the surface. With a flat surface, we like to say we have basically have a law of refraction. Law of refraction. The law of refraction is saying that the angle of incidence is equal to angle of reflection. Now, how you define angle of refraction? How you're going to define angle of incidence? All related with normal. At a flat surface, at a point, is a normal surface. Normal to the surface is a line drawn perpendicular to the surface. So in this case, this is normal, and the light ray, the incident ray, making the angle with the normal, we consider as instant angle, theta sub I. And the refracted ray and the normal making an angle is called angle of refraction. So in this case, for the refraction surface, for flat surface, then we have the angle of incidence equal to angle of refraction. So basically, we like to say theta sub I equal to theta refract. So this is calling the law of refraction. So cut. So now law of refraction, in each case, angle incidence for angle of reflection. The theta sub I equal to theta sub FL. Now, for any spherical surface, for this particular cases, we are talking about the convex spherical surface. When the incident ray coming in and hitting a point, because this is spherical surface, this line pass through the center. We consider is a normal. So this is a normal line. So for the incident ray making an angle with the normal line is called incident angle. And then the refract the light ray is the angle is making with the normal is called the angle of refraction. So consequently, again, you can apply the law of refraction, in which case theta sub I equal to theta sub FEL. Now, the other one, this is the convex spherical surface. Now we're talking about concave spherical surface. You do the same thing. Looking at the point of interception, and this is the incident ray hitting this point, and then you draw the center line, and then after the center line, then you should consider this is normal again. This again is normal. For this normal, the angle made between the normal and the incident ray is called incident angle, and the light ray making the refracted ray making with the normal is called angle of refraction. So again, the law of refraction can be applied for the concave spherical surface. It's calling it angle of incidence equal to angle of reflection, angle of refraction. So now when you come again with an irregular